Welcome to Sleep to Science. Tonight, we're exploring the true scale of cosmic reality. This journey stretches far beyond anything our daily experience prepares us for. When you look up at those scattered points of light decorating the night sky, what are you actually seeing? Most people assume they're gazing out at a modest collection of nearby stars floating in mostly empty space. That comfortable assumption couldn't be more wrong. Those innocent-looking pinpricks represent just the tiniest sample of something almost incomprehensibly vast. Picture standing at the edge of an ocean. Now imagine thinking you're looking at a small pond. Tonight, you'll discover how space telescopes recently finished counting the cosmic population. The numbers should humble every person alive. We'll trace how the universe has been playing the ultimate expansion game for nearly 14 billion years. You'll see how the cosmic background temperature surrounding us holds clues to the most extraordinary moment in cosmic history. We'll explore why 95% of everything that exists remains completely invisible and mysterious to us. So settle in. Before we begin, leave a quick note in the comments, where you're listening from, or one thought you're carrying tonight. I read them, and they genuinely help shape future journeys. If you'd like more nights like this, subscribe. Only if you enjoy these late-night journeys. Now let's begin. Space telescopes just finished the most ambitious cosmic headcount in human history. The results will blow your mind completely. Astronomers discovered that our observable universe contains approximately 2 trillion galaxies. Not million, not billion, trillion. That's roughly 285 galaxies for every person who has ever lived on Earth. Each galaxy operates like a massive stellar city. The small ones house around 100 million star residents. The galactic megacities contain over 1 trillion blazing nuclear furnaces. Our own Milky Way sits comfortably in the middle with about 400 billion stellar neighbors. Just one ordinary resident in this incomprehensibly vast cosmic population. Here's where the numbers become truly ridiculous. When you multiply 2 trillion galaxies by their average stellar populations, you get approximately 200 billion trillion individual stars. That's a number with 23 zeros after it. If every star was a grain of sand, you could bury the entire Earth under a layer 30 kilometers deep. Mount Everest would completely disappear under that cosmic sandbox. But here's the kicker. These galactic cities don't huddle together like earthly neighborhoods. They float through space separated by distances that make their own enormous sizes look tiny. A typical galaxy might stretch 100,000 light-years across. Its nearest galactic neighbor sits millions of light-years away. The galaxies themselves perform elaborate cosmic choreography. Some spiral like galactic hurricanes with arms of stars streaming outward from blazing centers. Others shine as brilliant elliptical beacons packed with ancient stellar populations. Still others slam together in gravitational crashes that last hundreds of millions of years. And here's the part that should really mess with your head. These 2 trillion galaxies represent only what our current instruments can actually detect. The real universe probably extends far beyond our observational limits. We live on one planet, orbiting one star in one galaxy among trillions. A cosmic address so absurdly remote it redefines what middle of nowhere actually means. What if space itself literally grows larger every single second? Right now, as you sit there reading this, something completely extraordinary is happening all around you. The universe isn't just expanding like a balloon being inflated. That comparison is way too simple for what's actually going on. Instead, space itself literally manufactures brand new cosmic real estate between galaxies. This process has been running nonstop for 13.8 billion years. Picture the ultimate cosmic escalator. Galaxies don't speed away from us by racing through existing space. The space between us and them actually grows bigger. It carries distant galaxies along like passengers on an accelerating moving walkway. The farther away a galaxy sits, the faster this spatial expansion hauls it away from us. Galaxies sitting 1 billion light-years away recede at 24,000 kilometers per second. Double the distance, double the recession speed. Now here's where cosmic expansion gets absolutely mind-bending. The most distant galaxies we can observe flee from us at over 90% the speed of light. Some galaxies actually recede faster than light without breaking Einstein's cosmic speed limit. How's that possible? They're not racing through space at impossible speeds. Space itself expands so rapidly at those distances that it creates separation velocities exceeding light speed. Pure geometric stretching makes this possible. The expansion follows a beautifully precise mathematical rule called Hubble's law. For every 3.26 million light-years of distance, recession velocity increases by exactly 70 kilometers per second. The universe operates like a perfectly calibrated machine for manufacturing distance and separation. What began as an incredibly dense, hot starting point has been stretching and cooling for nearly 14 billion years. The cosmic pressure cooker transformed into the vast, cold expanse surrounding us today. But astronomers recently discovered something that completely upended their expectations. They thought gravity would gradually slow down this universal stretching over billions of years. Instead, they found expansion is actually accelerating. Some mysterious force they call dark energy pushes against gravity and drives galaxies apart at ever-increasing rates. Imagine floating through space. You'd expect complete darkness, absolute silence, nothing but empty void stretching in every direction. That expectation is exactly wrong. Every cubic centimeter of seemingly empty space buzzes with invisible radiation. This cosmic background radiation bathes everything in a gentle warmth of 2.7 degrees above absolute zero. That sounds incredibly cold, and it is. But this temperature tells one of the most remarkable stories in cosmic history. This radiation represents the afterglow of creation itself. About 380,000 years after the Big Bang, the universe finally cooled enough for atoms to form. Before that moment, space blazed with temperatures of several thousand degrees, hot enough to keep electrons and protons flying around as superheated plasma soup. When the cosmic temperature dropped below 3,000 degrees, electrons finally stuck to protons. They created the first hydrogen atoms. This cosmic cooling event released a brilliant flash of light that filled the entire universe. That ancient light has been traveling through space ever since. It grows steadily cooler and redder as the universe expanded around it. What started as visible light now appears as microwave radiation, the same type that heats your leftover pizza, just much weaker. Every square inch of sky glows with this fossil light from when the universe first became transparent. We're literally surrounded by the leftover glow from cosmic dawn. Advanced satellites have mapped this background radiation with incredible precision. The temperature varies by tiny amounts across different regions of the sky. usually just a few 10,000ths of a degree difference. These microscopic hot and cold spots represent the seeds that eventually grew into today's cosmic web of galaxies and galaxy clusters. This cosmic microwave background provides our best baby picture of the universe. It shows us exactly what space looked like when the cosmos was just 380,000 years old, practically an infant compared to today's 13.8 billion year age. Every measurement confirms that our universe began as an incredibly hot, dense state. It has been expanding and cooling ever since. The cosmic deep freeze surrounding us preserves evidence of the most important event in cosmic history, the moment when light first traveled freely through space and the universe became the transparent realm we inhabit today. Here's a discovery that should terrify anyone who likes understanding reality. Everything we can see represents less than 5% of what actually exists. Every star, planet, galaxy, and cosmic gas cloud amounts to a cosmic rounding error. The remaining 95% of the universe consists of completely invisible stuff. It reveals itself only through its gravitational effects. We live in a cosmos dominated by mysterious substances that refuse to interact with light in any way we can detect. Dark matter makes up about 27% of cosmic reality. This invisible scaffolding outweighs all visible matter by more than 5 to 1. Galaxies couldn't exist without it. Stars and spiral arms should fly apart based on how fast they orbit galactic centers. The visible matter doesn't provide nearly enough gravitational glue to hold these cosmic structures together. Dark matter creates the invisible framework that keeps galaxies from ripping themselves apart through their own rotation. Even more bizarre is dark energy, which comprises roughly 68% of everything that exists. This mysterious force drives the accelerating expansion we discovered in distant supernova. Dark energy acts like cosmic anti-gravity. It pushes space apart at ever-increasing rates. Scientists have no idea what dark matter and dark energy actually are. Dark matter might consist of exotic particles that interact only through gravity. It could be primordial black holes formed in the early universe, or it might require completely new physics beyond our current understanding. Dark energy remains even more mysterious. It might represent the energy of empty space itself, or evidence that Einstein's theory of gravity needs modification on cosmic scales. This invisible empire reveals just how little we actually know about cosmic reality. Imagine trying to understand a vast city while being able to see only 5% of the buildings, roads, and residents. That's essentially our situation with the universe. The visible cosmos represents just the tiny fraction that happens to emit or absorb light. The rest remains hidden in plain sight. It controls cosmic evolution through gravitational effects we can measure but not directly observe. We live as cosmic tourists in a reality dominated by forces and substances that remain completely alien to our experience. Every galaxy rotation curve reminds us that we inhabit a universe far stranger than anything our visible light telescopes reveal. The invisible cosmic empire controls everything while revealing almost nothing about its true nature. Space might seem quiet and peaceful from our comfortable distance. The universe actually hosts the most violent ongoing fireworks display imaginable. Every single second, roughly 20 massive stars somewhere in the observable universe reach the end of their nuclear fuel supply. They explode as supernovae. These stellar death throes release more energy in minutes than our Sun will produce during its entire 10 billion year lifetime. The cosmic fireworks never stop. These aren't gentle stellar sunsets. When a star at least 8 times more massive than our Sun exhausts its nuclear fuel, the core collapses in less than a second. The resulting explosion blasts the star's outer layers into space at speeds of 30,000 kilometers per second. For a few weeks, a single supernova can outshine an entire galaxy containing hundreds of billions of normal stars. These cosmic bombs create shock waves that trigger new star formation in nearby gas clouds. The mathematics of stellar destruction are staggering. With 2 trillion galaxies and an estimated 20 supernova per second across the observable universe, the math adds up fast. Roughly 630 million stellar explosions occur every single year. Each explosion synthesizes and disperses heavy elements forged in the star's nuclear furnace: carbon, oxygen, silicon, iron, and dozens of other elements essential for rocky planets and life itself. Every atom in your body except hydrogen was manufactured inside a massive star and scattered through space by supernova explosions. But supernovae represent just the most spectacular cosmic fireworks. Stellar birth creates its own impressive light shows as gravitational collapse heats gas clouds to millions of degrees. Massive stars burn through their nuclear fuel so rapidly they live only a few million years. Cosmic mayflies that blaze brilliantly before exploding. The universe operates like a cosmic 4th of July celebration that's been running continuously for over 13 billion years. While we sleep peacefully on our small planet, massive stars across countless galaxies burn through their fuel reserves. They explode in spectacular finales that temporarily outshine billions of ordinary stellar neighbors. This endless stellar violence creates and disperses the chemical elements that make rocky planets and complex chemistry possible. Every breath you take contains atoms forged in stellar furnaces, atoms scattered by cosmic explosions occurring throughout the universe's long, violent, spectacular history. The cosmic fireworks continue right now as you read these words. Somewhere among those 2 trillion galaxies, another massive star just reached the end of its brief, brilliant life. It exploded with the force of 10 billion hydrogen bombs detonating every second for millions of years. The stellar violence never ends, and without it, none of us would exist. Every morning, the sun delivers a very special package to Earth. Sunlight streaming through your window just completed an 8-minute, 20-second journey across 150 million kilometers of empty space. That distance has a special name in astronomy, 1 astronomical unit, or AU for short. The universe's standard measuring stick for our solar system neighborhood. Most people don't realize how vast this seemingly modest distance actually is. Light travels at 300 million meters per second, fast enough to circle Earth's equator 7 times in just 1 second. Yet even at this ridiculous speed, sunlight needs more than 8 minutes to cross the gap between our star and our planet. During your morning coffee routine, you're seeing the sun as it appeared 8 minutes and 20 seconds ago. Every sunrise is actually a delayed broadcast from the cosmic past. This 150 million kilometer separation serves as Earth's cosmic sweet spot. Astronomers call it the habitable zone. Move Earth just 5% closer to the sun. Our oceans boil away like water in a pressure cooker. Shift us 15% farther out. Everything freezes solid into a cosmic ice ball. That precise distance maintains liquid water temperatures across billions of years. Earth won the solar system's ultimate real estate lottery. The Earth-Sun distance also creates our planet's yearly calendar. As Earth orbits along this 150 million kilometer radius, we complete one lap in exactly 365.25 days. Our elliptical path stretches roughly 940 million kilometers around its entire circumference. Earth races through space at about 107,000 kilometers per hour just to maintain its orbital position. We're all passengers on a cosmic racetrack that never slows down. This fundamental distance that defines our entire world represents just the first tiny step in solar system scale. The 150 million kilometers between Earth and Sun will serve as our measuring stick for exploring distances that grow increasingly mind-boggling. 1 AU might sound impressively large, but it's merely the opening act in our solar system's scale performance. Consider our solar system as a vast cosmic mansion. 8 permanent residents spread across an estate 9 billion kilometers wide. That's the diameter from the Sun to Neptune's orbit, roughly 60 times larger than the Earth-Sun distance that already seemed enormous. Picture yourself lying flat on a massive spinning disk if Earth sat 1 meter from a basketball-sized sun. Neptune would be lounging 60 meters away. The entire planetary family occupies a residential complex the size of multiple football fields. Each planet claims its own distinct neighborhood within this cosmic estate. Mercury huddles closest to the solar furnace at just 0.39 AU. It receives 7 times more solar radiation than Earth. Venus follows at 0.72 AU, trapped in a runaway greenhouse that could melt lead. Mars maintains a chilly residence at 1.5 AU, where water freezes most of the year. These inner planets cluster relatively close together like neighbors in a suburban cul-de-sac. Then comes the asteroid belt, essentially a cosmic fence separating the inner and outer neighborhoods. Beyond this rocky boundary, the outer planets spread across truly mind-boggling distances. Jupiter claims the prime outer real estate at 5.2 AU from the Sun. Saturn sits at 9.5 AU, roughly twice Jupiter's distance. Uranus lurks at 19 AU, while Neptune holds down the outer frontier at 30 AU from our central star. These outer planet distances create travel times that would test anyone's patience. Light from the Sun takes 43 minutes to reach Jupiter. Sunlight needs over 4 hours to illuminate Saturn's magnificent rings. By the time solar radiation reaches Neptune, more than 4 hours have passed since leaving the Sun's surface. Neptune experiences sunlight that left our star when you were probably eating lunch. The spacing between these planetary neighbors grows increasingly ridiculous in the outer solar system. Jupiter and Saturn sit about 4.3 AU apart. The gap between Saturn and Uranus spans nearly 10 AU. Uranus and Neptune are separated by 11 AU of mostly empty space. The outer planets live like cosmic hermits, each one isolated by distances that would take decades for even our fastest spacecraft to cross. Beyond Neptune's orbit lies one of the solar system's strangest neighborhoods, a cosmic deep freeze packed with leftover building materials from our solar system's construction. Welcome to the Kuiper Belt, a donut-shaped region of space that extends from about 30 to 50 AU from the Sun. This frozen wasteland houses tens of thousands of icy objects that have remained virtually unchanged for 4.6 billion years. Think of it as the solar system's ultimate storage locker, filled with primordial ice cubes. These Kuiper Belt objects represent cosmic fossils from when our solar system was still under construction. Most are mixtures of rock, ice, and frozen gases that never quite made it into full-fledged planets. They range from small building block-sized chunks to dwarf planets hundreds of kilometers across. Pluto, probably the most famous resident, stretches about 2,400 kilometers in diameter, roughly two-thirds the size of Earth's moon, but with a lot more attitude about being reclassified. The distances in the Kuiper Belt make Neptune seem like a next-door neighbor. Pluto orbits at an average distance of 39 AU from the Sun. Its elliptical path sometimes it closer than Neptune, and other times carries it nearly 50 AU away. At that distance, sunlight takes over 5.5 hours to arrive. The Sun appears no larger than a particularly bright star. High noon on Pluto feels more like twilight on Earth. What makes these frozen residents particularly fascinating is their pristine condition. Unlike the inner solar system, where planetary formation heated and transformed most materials, the Kuiper Belt remained cold enough to preserve the original ingredients. These icy time capsules contain water ice, methane, ammonia, and other compounds that represent the solar system's chemical starting materials. They're essentially cosmic archaeological specimens that scientists can study to understand how planets formed. Many Kuiper Belt objects follow highly elliptical orbits that occasionally send them plunging toward the inner solar system. When this happens, solar heating transforms these distant ice balls into spectacular comets. Comets with glowing tails that stretch millions of kilometers. Every comet you've ever seen probably originated in this frozen storage facility beyond Neptune's orbit. Deep in the outer darkness, far beyond where any planets dare to venture, lies the solar system's most remote region, the Oort cloud. This cosmic waiting room extends from about 2,000 AU all the way out to 100,000 AU from the Sun. That outer boundary sits roughly 1.6 light-years away, about one-third the distance to our nearest stellar neighbor. The Oort cloud essentially marks where our solar system ends and true interstellar space begins. The Oort cloud houses an estimated 1 trillion cometary nuclei in cold storage. These aren't the relatively nearby ice balls of the Kuiper Belt. These are the solar system's most distant residents. They orbit so far away that the Sun appears as nothing more than a particularly bright star among thousands. Temperatures hover just a few degrees above absolute zero. These cosmic outcasts spend most of their time in frozen hibernation. They wait millions of years between close approaches to the Sun. The scale of the Oort cloud defies earthly comprehension. Drive a car at highway speeds toward the outer edge. The journey would take roughly 12 million years. Light from the Sun takes over 1 year to reach the cloud's outer boundary. The entire sphere encompasses a volume so vast that it could easily contain thousands of solar systems like ours. None of them would interfere with each other. What makes the Oort cloud particularly remarkable is how it formed. These icy objects didn't start their lives in the distant outer darkness. Most began much closer to the Sun, in the region where the giant planets formed. Gravitational encounters with Jupiter, Saturn, Uranus, and Neptune gradually kicked these smaller objects into increasingly distant orbits, eventually flinging them into the cosmic outer suburbs. Occasionally, a passing star or galactic tide nudges an Oort cloud object enough to send it falling back toward the inner solar system. This cosmic billiard shot can take millions of years to complete. Eventually, it results in a spectacular comet display as the ancient ice ball approaches the Sun and develops its characteristic glowing tail. Every long-period comet we observe represents a cosmic messenger arriving from this distant, frozen waiting room. In 1977, NASA launched 2 robotic ambassadors on humanity's most ambitious cosmic road trip. Voyager 1 and Voyager 2 began racing toward the outer solar system. Their speed would take you from New York to Los Angeles in 10 minutes. Their mission: to visit the giant planets and then continue into the cosmic unknown. What they discovered about solar system scale should humble anyone who thinks space travel might be easy. Voyager 1 currently holds the record as humanity's most distant emissary. After 46 years of non-stop travel at roughly 61,000 kilometers per hour, it has covered approximately 24 billion kilometers. That's about 160 AU from the Sun, far beyond Neptune's orbit, past the Kuiper Belt, and well into the realm where the solar wind starts losing its battle against interstellar space. Yet even at this mind-boggling distance, Voyager 1 only recently escaped the Sun's direct influence. The spacecraft's escape reveals something profound about solar system scale. Our Sun's gravity extends much farther than most people imagine, while the planets orbit within 30 AU. The Sun's gravitational grip remains significant out to roughly 100,000 AU, the edge of the Oort cloud. Voyager 1's current position represents less than 0.02% of the distance to where the Sun's gravity finally becomes negligible compared to other stars. Here's the cosmic reality check that makes interstellar travel seem almost laughably difficult. At Voyager 1's impressive speed, reaching our nearest stellar neighbor would require approximately 73,000 years. That's longer than all of recorded human history. Even if we could build spacecraft 100 times faster than Voyager, the journey would still take over 700 years. The distances between stars transform our fastest technological achievements into cosmic snail mail. Voyager 1's journey also reveals the shocking emptiness of space. During its 46-year voyage, the spacecraft has encountered essentially nothing but vacuum punctuated by occasional wisps of interstellar gas. The space between planets contains maybe 1 atom per cubic centimeter. Interstellar space is even more empty, perhaps 1 atom per 10 cubic centimeters. Voyager is essentially racing through the universe's best attempt at creating perfect nothingness. The spacecraft continues transmitting data back to Earth using a 23-watt radio transmitter, about the same power as a refrigerator light bulb. That faint signal takes over 22 hours to travel from Voyager 1's current position back to Earth, even at the speed of light. By the time you receive a status update from humanity's most distant explorer, the information is already nearly a full day old. Voyager 1's epic journey illustrates the staggering scale challenge facing any civilization attempting to explore beyond their home star system. After nearly half a century of travel, humanity's fastest ambassador has barely begun to scratch the surface of interstellar distances. Proxima Centauri holds the title as our closest stellar neighbor. Frankly, it's not very neighborly at all. This red dwarf star sits 4.3 light-years away from Earth. That distance sounds modest until you realize what it actually means for anyone hoping to visit. Light itself, racing at 300 million meters per second, takes 4.3 years just to make the trip. It's the cosmic equivalent of living in a house. Your nearest neighbor requires a 4-year hike just to borrow a cup of sugar. Converting 4.3 light-years into more familiar units reveals the true absurdity of interstellar distances. Proxima Centauri sits roughly 40 trillion kilometers away from Earth. That's 40 followed by 12 zeros, a number so large it becomes essentially meaningless to human comprehension. Drive there at highway speeds. The journey would take approximately 48 million years. That's longer than dinosaurs ruled the Earth. Our current space technology makes this cosmic road trip seem even more hopeless. The Voyager spacecraft, humanity's fastest deep space travelers, cruise at about 61,000 kilometers per hour. At that impressive speed, reaching Proxima Centauri would require roughly 73,000 years. That's longer than our entire species has existed on Earth. Multiple ice ages would come and go. Entire civilizations would rise and fall. The pyramids would crumble to dust several times over. Even our most optimistic future propulsion concepts struggle with interstellar distances. Theoretical fusion rockets might achieve 10% the speed of light, roughly 108 million kilometers per hour. Such a spacecraft would still need 43 years to reach our nearest stellar neighbor. That's an entire human lifetime spent traveling through the cosmic void to visit one nearby star. The Parker Solar Probe is currently our fastest human-made object. It reaches speeds of 700,000 kilometers per hour when diving close to the Sun. Even at this blistering pace, Proxima Centauri remains a 6,500-year journey away. Interstellar travel transforms our most impressive technological achievements into cosmic crawling. The space between stars operates on scales that make human ambitions seem almost adorably naive. Take a cosmic census within 30 light-years of Earth. You'll discover something that should make urban planners weep. Approximately 400 stars spread across a volume of space so vast it defies comprehension. That stellar population density makes the most remote wilderness on Earth look like downtown Manhattan during rush hour. We live in the cosmic equivalent of a farming community. The neighbors are spread so far apart you need a telescope just to confirm they exist. Those 400 stellar neighbors occupy a spherical volume roughly 60 light-years across at its widest point. Picture a cosmic neighborhood where each house sits on a lot measuring several light-years on each side. The closest neighbors require multi-year hikes just to visit. Most residents never interact at all. It's the ultimate suburban sprawl taken to ridiculous extremes. The stellar demographics within our local neighborhood reveal just how antisocial space really is. About 75% of our stellar neighbors are red dwarf stars. Small, dim objects that barely qualify as proper suns. These cosmic wallflowers burn so faintly that most remain completely invisible to the naked eye despite being relatively nearby. Only about 30 stars within this entire 30 light-year radius shine brightly enough for ancient astronomers to notice and catalog. Even more sobering is the realization that we're actually living in a relatively crowded region of the galaxy. Our local stellar density runs about average for the galactic disk. Other regions of the Milky Way contain even fewer neighbors spread across even more ridiculous distances. Some stars in the galactic halo live in such cosmic isolation that their nearest neighbors sit hundreds of light-years away. The emptiness between these scattered stellar residents makes interstellar communication seem almost comically difficult. Radio signals traveling at light speed would take decades to reach even nearby stars. Decades more for any reply to return. A simple hello message sent to our closest neighbors would require human lifetimes for completion. Interstellar conversation makes snail mail look lightning fast. Every star in our galactic neighborhood enjoys a level of personal space that would make the most extreme hermit jealous. The average star claims roughly 300 cubic light years of cosmic real estate all to itself. Converting that volume into more familiar units reveals numbers that break human comprehension. About 2.4 septillion cubic kilometers per stellar resident. That's enough space to fit about 300 million solar systems, each one identical to ours. None of them would interfere with each other. Picture the ultimate cosmic suburbs where property lots stretch several light years in every direction. Each stellar resident sits at the center of a three-dimensional territory so vast. Light needs years just to travel from one property line to another. These aren't cozy neighborhood lots where you can wave to your neighbors across the fence. These are cosmic estates where neighboring stars remain virtually invisible despite burning as nuclear furnaces. Each one contains the mass of hundreds of thousands of Earths. The emptiness becomes even more staggering when you consider what fills all that space between stars. Mostly nothing. The interstellar medium contains perhaps 1 atom per cubic centimeter, a vacuum so perfect that our best laboratory equipment can't reproduce it. For comparison, air at sea level contains roughly 30 billion trillion atoms per cubic centimeter. The space between stars achieves a level of emptiness that makes our planet's atmosphere seem impossibly dense. This cosmic spacing creates some mind-bending perspectives on stellar collisions. When the Andromeda galaxy eventually crashes into the Milky Way in about 4.5 billion years, the two galactic populations will interpenetrate, almost entirely without any actual stellar collisions. Despite involving hundreds of billions of stars from each galaxy, the odds of any two stars actually hitting each other remain essentially zero. During this galactic merger, the stars will pass by like cosmic ships in the night. Each one maintains its splendid isolation. Even within dense star clusters, the most crowded stellar neighborhoods in the galaxy, individual stars maintain separations of several light weeks or light months. These packed stellar environments would still seem impossibly empty by human standards. The cosmic real estate market operates on scales where neighbors require telescopes to observe each other. Multi-generational space missions for casual visits. Let's imagine humanity develops fusion propulsion technology capable of accelerating spacecraft to 60,000 kilometers per second. That's roughly 20% the speed of light. This represents a massive technological leap beyond anything currently possible. It would require energy sources and materials that exist only in theoretical physics papers. Even with this hypothetical superdrive, the journey to Proxima Centauri would still require about 21 years. It would be continuous travel through the interstellar void. That 21-year minimum flight time assumes perfect acceleration, perfect navigation, and perfect reliability for 2 decades straight. More realistic mission profiles involving gradual acceleration and deceleration would extend the journey to 30 or 40 years minimum. Any interstellar mission becomes an inevitable multi-generational project. The people who launch the spacecraft will never see its arrival at the destination. The engineering challenges become truly ridiculous when you consider what such a mission would actually require. The spacecraft would need to carry enough fuel, food, and spare parts for several decades in space. Radiation shielding would need to protect passengers from cosmic rays and interstellar particles encountered at 20% light speed. Life support systems would need to operate flawlessly for decades without any possibility of Earth-based maintenance or resupply. Even more optimistic propulsion concepts run into the same fundamental problem of interstellar distances. Theoretical antimatter rockets might achieve 50% light speed, reducing the Proxima Centauri journey to about 8.6 years. But antimatter fuel represents the most expensive substance imaginable. Current estimates suggest that producing just 1 gram would cost trillions of dollars using existing technology. The fuel requirements for interstellar missions would bankrupt entire civilizations. Some scientists have proposed robotic probe missions using light sails pushed by powerful laser arrays. These ultra-lightweight spacecraft might reach 15 to 20% light speed, arriving at nearby stars within 20 to 30 years. But such probes would weigh only a few grams and zip past their targets in minutes. They would provide just brief glimpses of distant worlds before continuing into the cosmic darkness. The sobering reality is that interstellar travel isn't just technologically difficult. It's fundamentally limited by the physics of space and time. Even at significant fractions of light speed, the stars remain separated by distances that transform any interstellar mission into a civilization-defining undertaking. The space between stars operates on scales that make our cosmic ambitions seem almost quaintly optimistic. The space between stars achieves a level of emptiness so profound it makes Earth's best vacuum chambers seem like crowded nightclubs. Interstellar space averages about 1 atom per cubic centimeter, roughly 1 hydrogen atom floating alone in a volume the size of a sugar cube. For comparison, the air you're breathing contains approximately 30 billion trillion atoms in that same volume. The cosmic vacuum is so perfect that our most advanced laboratory equipment can't even approach these conditions. This near-perfect emptiness creates some bizarre physical conditions that exist nowhere on Earth. The interstellar medium has an average temperature of about 10 degrees above absolute zero, yet it contains so few particles that the concept of temperature barely applies. A thermometer placed in interstellar space would register the cosmic background radiation rather than any meaningful thermal energy from surrounding matter. It's cold, empty, and eerily quiet in the space between stars. The cosmic vacuum becomes even more impressive when you realize it extends across light years without interruption. Unlike Earth's atmosphere, which contains pockets of varying density, interstellar space maintains its emptiness consistently across distances that dwarf solar system scales. Traveling from one star to another means crossing light years of space containing essentially nothing but occasional atoms drifting in splendid isolation. Spacecraft venturing into interstellar space encounter this cosmic emptiness firsthand. During their decades-long journeys, the Voyager probes have detected particle densities so low. Collisions with interstellar atoms occur perhaps once every few hours. At these encounter rates, spacecraft could coast through interstellar space for millions of years. It would accumulate less material than you'd find in a single breath of Earth's atmosphere. The emptiness also affects how we detect and study distant objects. Light from other stars travels through this near-perfect vacuum for years or decades before reaching our telescopes. Unlike Earth's atmosphere, which distorts and absorbs incoming light, interstellar space provides almost perfectly clear views across galactic distances. The cosmic vacuum serves as the universe's ultimate optical laboratory. Yet even this seemingly perfect emptiness isn't completely empty. The interstellar medium contains traces of cosmic dust, complex molecules, and magnetic fields that play crucial roles in galactic evolution. Supernova explosions inject heavy elements into this sparse environment. Stellar winds carry material between star systems. Over millions of years, even the near vacuum of interstellar space accumulates enough matter to eventually condense into new generations of stars and planets. This cosmic emptiness reveals something profound about the universe's architecture. The space between stars isn't just empty. It's actively maintained in a state of emptiness by the enormous distances involved. Gravity operates on such vast scales that matter naturally spreads out into configurations where most space remains essentially vacant. We live in a universe where emptiness, not crowding, represents the natural state of cosmic real estate. Our galaxy operates like the universe's most impressive piece of architecture, a spiral disk so enormous that light itself needs 100,000 years just to travel from one edge to the other. The Milky Way stretches roughly 100,000 light-years in diameter. This makes it one of the larger spiral galaxies in our cosmic neighborhood. Picture this comparison. If our entire solar system was the size of a quarter, the Milky Way would stretch about 10 kilometers across. We live inside a cosmic structure that dwarfs solar system scales by factors that make previous distances seem almost quaint. That 100,000 light-year diameter contains approximately 400 billion individual stars, each one a nuclear furnace capable of supporting its own system of planets. Count one star per second without stopping. Cataloging our galaxy's entire stellar population would require over 12,000 years of continuous counting. The stellar density varies dramatically across different galactic regions. The crowded downtown core packs millions of stars into relatively small volumes. The sparse outer suburbs keep stellar neighbors separated by light years of mostly empty space. The galaxy's spiral structure creates one of the most beautiful architectural patterns in the universe. 4 major spiral arms waned outward from the central region like cosmic hurricanes frozen in slow motion. These aren't solid structures, but rather density waves that sweep around the galactic disk. They compress gas and trigger star formation as they pass. The spiral pattern persists for billions of years. Individual stars drift in and out of the arms during their long orbital journeys around the galactic center. What makes the galactic scale truly mind-boggling is the realization that this enormous structure rotates as a coordinated unit. The entire 100,000 light-year disk spins around its central axis, though not like a rigid wheel. Different regions orbit at different speeds, creating a complex dance where inner areas complete multiple rotations while outer regions slowly lumber through single orbits. This differential rotation has been ongoing for over 13 billion years, gradually winding the spiral arms tighter while maintaining the galaxy's overall structural integrity. Light from the galactic center takes 26,000 years to reach our solar system's location in the outer suburbs. We see the central regions as they appeared when early humans were just learning to use stone tools. The light reaching us tonight from the galaxy's far edge began its journey when Earth was still dominated by dinosaurs. We live inside a cosmic time capsule where different regions reveal their past conditions rather than their current state. Deep within our galaxy's central bulge lurks one of the universe's most terrifying objects, a supermassive black hole containing the mass of 4 million suns compressed into a region smaller than our solar system. Sagittarius A star, as astronomers call this cosmic monster, exerts gravitational dominance over our entire galactic neighborhood. It sits 26,000 light-years away from Earth. This central black hole represents the gravitational anchor that holds our entire galaxy together. It orchestrates the orbital dance of hundreds of billions of stars. The scale of this central black hole challenges human comprehension. 4 million solar masses concentrated into a volume roughly the size of Mercury's orbit. It creates gravitational fields so intense they warp space and time into pretzels. Near the black hole's event horizon, gravity becomes so powerful that time itself slows to a crawl compared to distant regions. Material falling into this cosmic maelstrom accelerates to significant fractions of light speed before disappearing forever behind the point of no return. Despite its enormous mass, Sagittarius A star remains completely invisible except for its gravitational effects on nearby stars. Astronomers can track individual stars orbiting this central monster with periods ranging from decades to centuries. Some stellar residents venture so close to the black hole that they reach orbital speeds of several percent light speed, fast enough to complete orbits around our entire solar system in just a few hours. These high-speed stellar residents provide the best evidence for the black hole's existence and allow precise measurements of its incredible mass. The central black hole's gravitational influence extends throughout the entire galaxy. Its direct effects remain negligible at our distant solar system location. Sagittarius A star helps determine the overall structure and rotation pattern of the galactic disk. Computer simulations suggest that galaxies without central supermassive black holes develop dramatically different spiral patterns and stellar distributions. Our galaxy's beautiful architecture exists partly because of the gravitational organizing influence of this central monster. What makes this cosmic situation particularly remarkable is the delicate gravitational balance involved. The central black hole contains enough mass to significantly influence galactic structure, yet it represents only about 0.001% of the galaxy's total mass. It's like having a cosmic puppet master that controls the behavior of hundreds of billions of stars. It represents just a tiny fraction of the overall system. Our galaxy demonstrates the universe's most impressive feat of cosmic urban planning. It crams 400 billion stars into a disk so flat it makes paper look thick. The Milky Way's spiral disk stretches 100,000 light-years across but measures only about 1,000 light-years thick. That's a thickness-to-diameter ratio of roughly 1 to 100. Scale our galaxy down to the size of a dinner plate. It would be thinner than a sheet of paper. This extreme flatness creates one of the most remarkable architectural achievements in the known universe. The stellar residents organize themselves into distinct vertical neighborhoods within this cosmic pancake. Most stars, including our Sun, cluster within a few hundred light-years of the galactic midplane. the galaxy's equivalent of ground level. This central layer contains the youngest, most active stellar populations along with most of the galaxy's gas and dust. Above and below this stellar main street, older star populations gradually thin out. Eventually you reach the nearly empty regions far above and below the galactic disk. What keeps this cosmic pancake from collapsing into an even flatter structure or expanding into a spherical blob? The answer lies in a delicate balance between gravitational attraction and rotational motion. Gravity constantly pulls all stellar residents toward the galactic center and toward the midplane. Meanwhile, the galaxy's rotation provides the centrifugal force needed to prevent complete gravitational collapse. These competing forces reach equilibrium at specific heights above and below the midplane. They create stable orbital zones where stars can maintain their vertical positions for billions of years. The extreme flatness creates some mind-bending perspectives for galactic residents. From our position within the disk, we see the galaxy edge on as that familiar band of light stretching across Earth's night sky. Stars lying within the disk appear scattered across the celestial dome. The disk itself appears as a bright river of combined starlight. View our galaxy from far above or below. It would appear as a magnificent spiral pattern with clearly defined arms and a bright central bulge. Our edge on perspective makes it impossible to see the galaxy's overall spiral structure from our location within it. The galactic disk's thinness also explains why astronomical observations beyond our local galactic neighborhood become so challenging. Dust lanes within the disk block visible light from more distant regions. They create what astronomers call the zone of avoidance, where optical telescopes can't penetrate the cosmic fog. Only infrared and radio observations can peer through the galactic plane to reveal structures on the galaxy's far side. Right now, as you sit reading this, you're racing through space at 220 kilometers per second on the universe's longest roller coaster ride. Our entire solar system orbits the galactic center at roughly 800,000 kilometers per hour. Fast enough to circumnavigate Earth's equator in just 3 minutes. Yet even at this mind-boggling speed, completing one lap around our galactic neighborhood requires approximately 220 million years. Welcome to the cosmic marathon that makes every other journey seem like a quick sprint to the corner store. This galactic year represents one of the universe's most patient timekeeping systems. Since Earth formed 4.6 billion years ago, our solar system has completed only about 20 trips around the galactic racetrack. The dinosaurs lived and died during just the last fraction of our current lap. All of human civilization fits into roughly the final 0.0002% of our most recent galactic orbit. We live our entire species' history during what amounts to a cosmic eye blink of our current journey around the galaxy. The orbital mechanics governing this galactic marathon create one of astronomy's most puzzling mysteries. Common sense suggests that stellar residents closer to the galactic center should orbit faster than those in the outer suburbs. Just like planets in our solar system. Mercury races around the Sun in 88 days, while distant Neptune requires 165 years. But our galaxy defies these expectations completely. Stars maintain roughly similar orbital speeds, regardless of their distance from the galactic center. A phenomenon that led to the discovery of dark matter. Our solar system's current position places us in the galactic equivalent of suburban commuter traffic. We orbit within the Orion Spur, a minor spiral arm that connects two of the galaxy's major spiral highways. We cruise along our 220 million year orbital path. We periodically drift into and out of these spiral arms like a car changing lanes on a cosmic freeway. Each passage through a spiral arm exposes our solar system to increased radiation from young massive stars. It brings higher risks from supernovae explosions in active star-forming regions. The galactic orbital period also affects Earth's long-term climate patterns in subtle ways. Our solar system's vertical motion relative to the galactic plane follows a roughly 64 million year cycle. It carries us above and below the dusty midplane region where most cosmic debris accumulates. Some researchers suggest this galactic motion might influence the frequency of comet impacts and cosmic ray exposure, potentially affecting mass extinction events in Earth's biological history. What makes this cosmic marathon particularly remarkable is its incredible consistency across billions of years. Our solar system has maintained a relatively stable orbit for its entire 4.6 billion year existence. That is despite gravitational interactions with other stars, passages through spiral arms, and encounters with interstellar gas clouds. We're passengers on a cosmic train that has been running on schedule for longer than complex life has existed on Earth. Earth's cosmic address places us in the galactic equivalent of farmland, roughly 26,000 light-years from where most galactic action occurs. Our solar system occupies a modest position about halfway between the galaxy's blazing downtown core and its dark outer frontier. In galactic terms, we live in suburban sprawl that's neither central nor remote, comfortably isolated from the chaotic urban core while remaining close enough to benefit from the amenities of galactic civilization. This 26,000 light-year distance from the galactic center provides crucial advantages for planetary habitability. Stars packed in the galaxy's crowded central regions experience harsh radiation from the supermassive black hole. They face frequent disruption from massive stellar explosions and gravitational chaos that regularly disrupts planetary orbits. These downtown galactic neighborhoods remain hostile to the development and persistence of complex life. Meanwhile, the galaxy's outer suburbs lie too far from the chemical enrichment provided by dying stars. This makes rocky planet formation extremely difficult. Our location in the Orion Spur provides the best of both worlds, a minor spiral arm connecting two major galactic highways. We enjoy relatively peaceful conditions far from the galaxy's most violent neighborhoods, yet we remain close enough to benefit from heavy elements synthesized by previous generations of massive stars. This galactic habitable zone extends roughly from 20,000 to 30,000 light-years from the center. It encompasses the region where conditions remain stable enough for billions of years of planetary evolution. The view from our galactic suburbs creates a unique astronomical perspective that shapes how we understand the universe. Our edge-on view of the galactic disk appears as that familiar band of light stretching across Earth's night sky, the Milky Way that ancient cultures interpreted as everything from a cosmic river to the pathway of souls. Stars scattered across the celestial dome represent our local galactic neighborhood. The dense star fields toward the galactic center reveal the direction of our galaxy's downtown core. Our suburban address also influences the pace of cosmic evolution in our local region. Star formation proceeds at a modest rate in our galactic neighborhood, active enough to provide chemical enrichment from dying stars, not so vigorous that frequent supernovae sterilize planetary surfaces with deadly radiation. We live in a cosmic sweet spot where stellar evolution proceeds at the perfect pace for complex chemistry. It allows planetary development to flourish over billions of years. Perhaps most remarkably, our seemingly ordinary galactic address has remained stable for our solar system's entire 4.6 billion year history. Orbital motion carries us through different galactic regions. Passing stars add occasional gravitational disturbances. Yet we've maintained residence in the same general cosmic neighborhood throughout Earth's entire evolutionary history. Our galactic zip code has provided the stable environmental conditions necessary for life to emerge and evolve. It eventually developed the intelligence to contemplate its place in this vast cosmic architecture. Andromeda Galaxy sits 2.5 million light-years away from the Milky Way. That distance makes previous cosmic scales seem almost neighborly by comparison. This intergalactic gulf represents the closest thing our galaxy has to a next-door neighbor. Yet the space between us could comfortably fit about 50 galaxies the size of the Milky Way. None of them would touch each other. We live in a cosmic neighborhood where even the nearest neighbors require multi-million-year hikes just to say hello. Light from Andromeda began its journey to Earth when early human ancestors were just learning to walk upright. Every photon reaching our telescopes tonight carries information about how Andromeda appeared 2.5 million years ago, long before modern humans existed. We see our galactic neighbor not as it is, but as it was when our planet was populated by entirely different species. Species living in dramatically different climates. Intergalactic astronomy inevitably becomes a form of cosmic archaeology. The space separating us from Andromeda contains mostly nothing. This intergalactic void averages perhaps 1 atom per cubic meter. A vacuum so perfect it makes interstellar space look crowded. Crossing this cosmic canyon would require traveling through 2.5 million years worth of emptiness at light speed. You'd encounter essentially zero matter along the way. It's the ultimate example of cosmic real estate, where the space between properties vastly exceeds the size of the properties themselves. Despite this enormous separation, Andromeda and the Milky Way are actually approaching each other under mutual gravitational attraction. These two galactic giants are currently racing toward a collision at roughly 400,000 kilometers per hour. But don't pack your evacuation bags yet. This intergalactic smash-up won't occur for approximately 4.5 billion years. Even at cosmic scales, covering 2.5 million light-years takes an impressively long time. What makes this intergalactic distance particularly mind-boggling is the realization that Andromeda represents our closest major galactic companion. Beyond Andromeda, the next large spiral galaxy sits over 10 million light-years away. The space between major galaxies operates on scales that dwarf even the impressive distances we've encountered within galactic neighborhoods. Intergalactic space reveals just how isolated individual galaxies really are in the cosmic ocean of mostly empty darkness. When the eventual Andromeda and Milky Way collision finally occurs, the two spiral disks will interpenetrate almost completely without any actual stellar collisions. Despite involving roughly 1 trillion stars total, the vast spaces between individual stellar residents mean that direct star-to-star impacts remain essentially impossible. Even during the ultimate galactic merger, the cosmic real estate market maintains its commitment to ridiculous amounts of personal space for every stellar resident. About 54 million light-years from Earth lies one of the universe's most impressive urban development projects, the Virgo Cluster. Roughly 2,000 galaxies have gathered into the cosmic equivalent of downtown Manhattan. This galactic megacity spans approximately 15 million light-years across and contains more stellar residents than you could count in several lifetimes. If individual galaxies represent cosmic cities, then the Virgo Cluster operates as the universe's ultimate metropolitan area. Galactic neighbors actually live close enough to influence each other's development. The cluster's central region houses some genuine galactic celebrities. The giant elliptical galaxy M87 sits near the downtown core, containing approximately 1 trillion stars. It harbors a central black hole with the mass of 6.5 billion suns. This galactic skyscraper towers over its spiral neighbors like a cosmic Empire State Building. It dominates the cluster's gravitational and social landscape. M87 has grown to its enormous size by systematically cannibalizing smaller galaxies that wandered too close to the cluster's central regions. What makes the Virgo Cluster particularly remarkable is how gravitational interactions reshape its galactic residents. Spiral galaxies entering the cluster's crowded downtown regions gradually lose their star-forming gas. This happens through interactions with hot intergalactic plasma and through gravitational stripping by larger neighbors. These cosmic gentrification processes transform vibrant spiral cities into elderly elliptical suburbs. Suburbs populated primarily by older stellar residents. The cluster environment actively sculpts galactic architecture through billions of years of gravitational urban planning. The cluster's gravitational field affects our entire local group of galaxies. This includes the Milky Way, Andromeda, and their various satellite companions. We're slowly falling toward the Virgo Cluster's gravitational embrace at roughly 600 kilometers per second. Completing the journey would require several billion years. Our galactic neighborhood exists within the Virgo Cluster's vast sphere of gravitational influence. This makes us cosmic suburbanites in an even larger metropolitan area than we previously realized. The space between galaxies within the Virgo Cluster contains surprisingly active neighborhoods. Hot plasma with temperatures of tens of millions of degrees fills the intergalactic medium. It glows brightly in X-ray wavelengths while remaining completely invisible to human eyes. This superheated cosmic atmosphere contains as much mass as all the visible stars within cluster galaxies combined. The cluster operates like a cosmic hot tub where galactic residents soak in a bath of million-degree plasma. Galaxy clusters like Virgo represent the largest gravitationally bound structures in the universe. Beyond cluster scales, cosmic expansion becomes stronger than gravitational attraction. This prevents even larger structures from forming. The Virgo Cluster shows us the ultimate limit of cosmic urban development, the largest possible downtown area where galaxies can gather and maintain stable neighborhoods across billions of years of cosmic evolution. Between the universe's galactic cities lie regions so empty they make intergalactic space look crowded by comparison. These cosmic voids stretch for hundreds of millions of light-years while containing essentially no galaxies at all. The BOHT's void, one of the largest known examples, spans roughly 500 million light-years across while housing perhaps 60 galaxies total. For comparison, A typical region of that size should contain approximately 50,000 galaxies. It's as if someone carved out a spherical chunk of the universe and forgot to put anything inside. These cosmic deserts challenge our understanding of how matter organized itself after the Big Bang. Computer simulations suggest that early density fluctuations in the primordial universe eventually grew. They became the cosmic web structure we observe today, a network of galaxy filaments separated by vast empty regions. The voids represent areas where initial matter density fell slightly below average. This caused material to gradually drain away toward denser regions over billions of years of gravitational evolution. Traveling through a cosmic void would provide the ultimate sensory deprivation experience. A hypothetical spacecraft crossing the BOHT's void would encounter essentially empty space for hundreds of millions of years, even at light speed. The few lonely galaxies scattered throughout such regions sit in isolation. Their nearest galactic neighbors lie tens of millions of light-years away. These cosmic hermits developed in environments so empty that normal galactic evolution processes barely applied. The scale of cosmic voids becomes even more staggering when you realize they occupy most of the universe's volume. Galaxy clusters and filaments represent just the cosmic scaffolding surrounding much larger empty territories. We live in a universe where emptiness, not matter, claims the vast majority of cosmic real estate. The cosmic web resembles a three-dimensional soap bubble structure. Galaxies huddle along the bubble walls, while enormous hollow regions dominate the interior space. What makes cosmic voids particularly mysterious is their almost perfect emptiness. Unlike intergalactic space within galaxy clusters, which contains hot plasma and diffuse matter, the voids approach true cosmic vacuum. They do so across mind-boggling volumes. These regions contain so little matter that their gravitational effects remain negligible compared to surrounding galaxy concentrations. They represent the universe's most successful experiments in manufacturing absolutely nothing across distances that challenge comprehension. Recent observations suggest that cosmic voids continue expanding as the universe ages. Dark energy affects void regions more strongly than matter-dense areas. This causes empty regions to grow even emptier, while galaxy concentrations become more isolated. The cosmic desert is getting bigger and more desolate as the universe evolves. It gradually transforms our cosmos into an increasingly lonely place where islands of matter drift apart through ever-expanding oceans of nothingness. Edwin Hubble discovered something in the 1920s that fundamentally changed our understanding of cosmic architecture. The farther away a galaxy sits from Earth, the faster it recedes from us through expanding space. This relationship follows a beautifully simple mathematical rule. For every 3.26 million light-years of additional distance, recession velocity increases by exactly 70 kilometers per second. It's like the universe operates according to a cosmic speed limit law. Your distance from Earth directly determines how fast you're required to flee. This Hubble's law creates a cosmic hierarchy of recession speeds that grows increasingly dramatic with distance. Galaxies 100 million light-years away recede at roughly 2,200 kilometers per second. That is about 0.7% of the speed of light. Double the distance to 200 million light-years. The recession speed doubles to 4,400 kilometers per second. Galaxies sitting 1 billion light years away race away from us at 22,000 kilometers per second, roughly 7% light speed. The universe enforces a strict relationship between cosmic real estate location and mandatory departure velocity. The mathematical precision of Hubble's law reveals something profound about space itself. Galaxies aren't racing through existing space at these incredible speeds. Instead, the space between us and distant galaxies literally expands. It carries galactic passengers along like cosmic escalators operating at different speeds depending on distance. The expansion rate remains constant throughout space. This creates the illusion that Earth occupies a special central position when actually every galaxy observes the same pattern from its own perspective. This cosmic expansion law allows astronomers to use recession velocity as a direct distance measurement tool. Measure how fast a galaxy recedes. You automatically know how far away it sits. The universe provides its own cosmic measuring stick where speed equals distance divided by the Hubble constant. This relationship transforms velocity measurements into cosmic cartography. It allows astronomers to map the three-dimensional structure of the universe across billions of light years. But here's where Hubble's law becomes truly mind-bending. At distances approaching 13 billion light-years, galaxies recede at speeds approaching the speed of light itself. Beyond about 14 billion light-years, recession velocities exceed light speed through pure geometric expansion. These ultra-distant regions become fundamentally unobservable because their light can never catch up with the expanding space carrying them away from us. Hubble's law defines the ultimate cosmic horizon beyond which the universe becomes forever invisible. The law also means that our observable universe has been steadily shrinking in terms of accessible cosmic real estate. Galaxies that we can see today will eventually recede beyond our observational horizon as cosmic expansion accelerates. Future astronomers will inherit an increasingly empty-looking universe where fewer and fewer galaxies remain visible from any given location. Hubble's law ensures that cosmic loneliness increases with time as the universe carries its contents apart through the relentless expansion of space itself. The most distant galaxies visible to our telescopes appear as they existed when the universe was just a cosmic toddler. It was less than 1 billion years old, compared to today's mature age of 13.8 billion years. Light from these ancient galactic nurseries has been traveling through expanding space for over 13 billion years. It carries baby pictures of cosmic evolution across distances so vast they challenge the very meaning of far away. These ultra-distant observations transform astronomy into cosmic archaeology. Greater distance equals deeper time. Galaxies at redshift z equals 10 or higher appear dramatically different from mature spiral and elliptical galaxies we observe in our cosmic neighborhood. These cosmic infants show up as small, irregular blobs containing intense star formation activity. They lack the organized structure that develops over billions of years of gravitational evolution. They represent the universe during its wild teenage years. Galaxy formation proceeded through chaotic mergers and violent star formation episodes rather than the sedate evolution we observe in nearby mature systems. The light from these primordial galaxies has been stretched to extreme wavelengths. What started as visible starlight now appears as infrared radiation by the time it reaches our telescopes. This cosmic redshift occurs because the space through which light travels has expanded by factors of 10 or more during the photon's multi-billion-year journey. Studying these ancient systems requires infrared space telescopes capable of detecting light that has been cosmologically shifted far beyond what human eyes can perceive. What makes these distant observations particularly remarkable is that they show us the universe during its phased transition from cosmic dark ages to the era of galaxy formation. The first billion years after the Big Bang represent a cosmic renaissance, when the initially smooth universe developed the lumpy structure we observe today. These distant galaxy observations capture the moment when gravity finally organized primordial matter into the first large-scale structures. They could form stars and support complex chemistry. The James Webb Space Telescope recently pushed these observations to even more extreme distances. It may have detected galaxies that formed just 400 million years after the Big Bang. These cosmic archaeological specimens reveal surprisingly massive and mature galaxy structures existing much earlier than theoretical models predicted. The universe apparently organized itself into complex galactic architectures faster than astronomers expected. This suggests that cosmic evolution proceeded more rapidly during the universe's youth. These ultra-distant observations also provide the best evidence for cosmic expansion and the finite age of the universe. The fact that we can see galaxies from the cosmic past proves that light has had time to travel from distant regions. This sets fundamental limits on how long the universe has existed. The most distant observable galaxies sit near the cosmic microwave background, the ultimate baby picture showing the universe at just 380,000 years old when it first became transparent to light. Beyond that distance, we're literally looking at the moment of cosmic dawn when the universe emerged from its initial opaque state. Light could travel freely through space for the first time in cosmic history. We live inside the universe's ultimate snow globe, a perfectly spherical boundary that extends 46.5 billion light-years in every direction from Earth. This cosmic horizon represents the absolute limit of what we can ever observe. It creates a bubble of visible reality beyond which the universe becomes forever hidden from our view. Wait, how can we see 46.5 billion light-years if the universe is only 13.8 billion years old? Welcome to one of cosmology's most mind-bending concepts. Expanding space makes distances larger than time should allow. The observable universe's boundary exists not because space runs out, but because light hasn't had enough time to reach us from more distant regions. Picture the ultimate cosmic mail system where letters take billions of years for delivery. We only receive mail from regions close enough for postal service to complete the journey since the universe began. Everything beyond our cosmic postal zone remains forever cut off from communication. No matter how long we wait or how powerful our telescopes become. What makes this boundary particularly strange is that it's not a physical wall, but rather a horizon defined by cosmic expansion. Light from the most distant observable regions began its journey when the universe was very young and compact. During the billions of years required for that light to reach us, space itself expanded dramatically. It stretched the distance between us and the light source. By the time ancient photons arrive at our telescopes, their points of origin have moved much farther away than light could have traveled in the available time. This cosmic horizon creates the ultimate cosmic perspective trick. Every observer in the universe sits at the center of their own 46.5 billion light-year bubble of observable reality. Aliens living in the Andromeda galaxy see their own cosmic horizon centered on their location. They have their own collection of observable galaxies that partially overlaps but differs significantly from our visible universe. The cosmic horizon is personal to every observer. It creates billions of different overlapping views of the same underlying cosmic reality. The boundary of our observable universe represents one of the most profound limits in science. Unlike technological barriers, this cosmic horizon stems from the physics of space and time. It also stems from the finite speed of light. No amount of technological advancement can extend our view beyond this ultimate boundary. We're permanently trapped inside our cosmic snow globe. We can see only the fraction of reality that light has had time to reveal since the universe began. What lies beyond our cosmic horizon remains one of the ultimate scientific mysteries. The universe almost certainly extends far beyond what we can observe. It potentially contains infinitely more galaxies, stars, and perhaps even different physical conditions than exist within our observable bubble. We're cosmic prisoners of our own light cone, forever limited to studying just the portion of reality that happens to be visible from our particular location in space and time. Surrounding us in every direction lies the most ancient light in the universe, a faint glow that began its journey when the cosmos was just 380,000 years old. This cosmic microwave background radiation maintains a nearly uniform temperature of 2.725 degrees above absolute zero. It makes it the coldest thing you can observe while also being the oldest electromagnetic radiation in existence. Every square inch of sky glows with this fossil light from when the universe first became transparent. It creates the ultimate cosmic baby picture that preserves evidence of our universe's earliest readable moment. Before this cosmic dawn, the universe existed in a completely opaque state. Light couldn't travel more than a few centimeters before being absorbed and re-emitted by the dense plasma soup of free electrons and protons. The entire cosmos blazed at temperatures of several thousand degrees, hot enough to keep atoms from forming while maintaining conditions similar to the interior of stars. This cosmic fog blocked any light from traveling significant distances. It made the early universe fundamentally unobservable using electromagnetic radiation. The cosmic microwave background marks the moment when the universe finally cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. This cosmic phase transition is called recombination. It made the universe transparent to light around 380,000 years after the Big Bang. The brilliant flash that accompanied this cosmic clearing event filled the entire universe with radiation. That radiation has been traveling through space ever since. It grows steadily cooler and redder as cosmic expansion stretched its wavelengths from visible light into the microwave portion of the electromagnetic spectrum. Advanced satellite missions have mapped this background radiation with incredible precision. They reveal temperature variations of just a few millionths of a degree across different regions of the sky. These tiny fluctuations represent the gravitational seeds that eventually grew into today's cosmic web of galaxies and galaxy clusters. Slightly warmer spots in the cosmic microwave background correspond to regions that were slightly denser in the early universe. They provided gravitational seeds that attracted additional matter over billions of years until they became the massive structures we observe today. This ancient radiation provides our most direct observational evidence for the Big Bang theory and cosmic inflation. The nearly perfect blackbody spectrum and uniform temperature distribution match theoretical predictions with extraordinary precision. They confirm that the observable universe began in an extremely hot, dense state before expanding and cooling to its current condition. The cosmic microwave background represents the ultimate forensic evidence for cosmic evolution. It preserves information about physical conditions that existed when the universe was roughly 100,000th its current age. The James Webb Space Telescope represents humanity's most ambitious attempt to peer as far back in cosmic time as current technology allows. This $10 billion cosmic time machine can observe galaxies located up to 13.5 billion light-years away. It reveals the universe as it appeared when the cosmos was less than 400 million years old. Webb's revolutionary infrared vision allows it to detect light that has been cosmologically redshifted far beyond what human eyes can perceive. It transforms ancient visible starlight into infrared radiation that requires space-based detection systems. Webb's extraordinary capabilities stem from its massive 6.5-meter primary mirror. It also relies on ultra-sensitive infrared detectors that operate at temperatures just a few degrees above absolute zero. The telescope orbits the Sun at the L2 Lagrange point, roughly 1.5 million kilometers from Earth. There it maintains a constant view of deep space while remaining shielded from solar radiation by its tennis court-sized sunshade. This cosmic observatory can detect infrared radiation so faint that it would be like spotting a candle flame on the moon from Earth's surface. The telescope's most distant observations reveal the universe during its cosmic renaissance, the period when the first large galaxies were forming and beginning to illuminate the cosmic dark ages. These primordial galactic nurseries appear surprisingly massive and organized for such early cosmic times. They challenged theoretical models that predicted more gradual structure formation. Webb's observations suggest that gravity organized matter into complex galactic architectures much faster than astronomers expected during the universe's youth. What makes Webb's observations particularly groundbreaking is their detail. Webb can study the detailed properties of individual galaxies that existed when the universe was less than 5% its current age. Previous telescopes could only detect these distant systems as faint smudges. But Webb can analyze their stellar populations, star formation rates, and chemical compositions. These measurements reveal that early galaxies contained surprisingly high concentrations of heavy elements. This indicates that previous generations of massive stars had already lived, died, and enriched the cosmic environment with synthesized elements. The telescope's infrared capabilities also allow it to peer through cosmic dust that blocks visible light observations. This dust-penetrating vision reveals hidden star formation activity in distant galaxies. It provides clearer views of galactic cores and stellar nurseries. Webb can observe cosmic phenomena that remain completely invisible to optical telescopes. It opens entirely new windows on galactic evolution and stellar formation processes across cosmic history. Despite its revolutionary capabilities, even Webb approaches fundamental physical limits on astronomical observation. The most distant galaxies it can detect sit near the epoch when the first stars began forming, roughly 100 to 400 million years after the Big Bang. Beyond this era, the universe contained no stars or galaxies to observe, just primordial gas clouds slowly condensing under gravitational collapse. Webb represents the current pinnacle of observational astronomy. It pushes technology to its limits while revealing that we're approaching the ultimate boundary of what electromagnetic radiation can teach us about cosmic history. At the extreme edge of observational astronomy lies a cosmic frontier marked by redshift Z=11, a zone where galaxies appear so ancient and distant that their light began its journey just 400 million years after the Big Bang. These primordial systems represent some of the first large structures to condense out of the cosmic dark ages. They show when the universe transitioned from a realm of simple hydrogen and helium gas into a cosmos capable of supporting complex stellar chemistry and galactic architecture. Detecting these cosmic fossils requires pushing observational technology to its absolute limits. The redshift measurement Z=11 means that the universe expanded by a factor of 12 during the time required for light to travel from these distant galaxies to our telescopes. What started as visible blue and ultraviolet starlight has been stretched to infrared wavelengths longer than what human eyes can detect. These galaxies appear not as they exist today. They've likely evolved into massive elliptical systems or merged with other galaxies. But as they appeared during the universe's cosmic childhood, when structure formation was just beginning, galaxies at redshift Z=11 reveal the universe during its phase transition from cosmic simplicity to complexity. During the first 400 million years after the Big Bang, gravity gradually collected primordial matter into increasingly dense concentrations. Eventually, they reached the critical thresholds necessary for triggering the first episodes of massive star formation. These initial stellar generations synthesized the first heavy elements heavier than hydrogen and helium. They began the cosmic chemical enrichment that would eventually enable rocky planet formation and complex chemistry. The extreme faintness of these Z=11 galaxies makes detection extraordinarily challenging. They appear roughly 10 billion times fainter than the dimmest stars visible to naked eye observation. This requires the combined power of space-based infrared telescopes and gravitational lensing by foreground galaxy clusters to achieve sufficient magnification for detailed study. Many confirmed detections require dozens of hours of observation time on the world's most powerful telescopes just to collect enough photons for reliable measurement. What makes these distant observations particularly valuable is their ability to test theoretical models of early cosmic evolution. Computer simulations predict specific relationships between galaxy mass, star formation rate, and chemical composition during the first billion years after the Big Bang. Observations of Z=11 galaxies provide direct measurements of these properties. They allow astronomers to compare theoretical predictions with actual cosmic history. Some recent discoveries have revealed surprisingly massive and chemically enriched galaxies existing earlier than models predicted. The redshift Z=11 frontier represents more than just a measurement milestone. It marks our approach to the ultimate observational boundary where electromagnetic astronomy becomes impossible. beyond redshift z equals 15 or z equals 20. The universe contained no stars or galaxies to observe, just primordial gas clouds slowly condensing under gravitational collapse. These ultra-high redshift observations bring us tantalizingly close to witnessing cosmic dawn itself. The moment when the first stars began converting primordial matter into the heavy elements that make planets and life possible. Beyond our observable universe's 46.5 billion light-year boundary lies something that should terrify anyone who likes knowing things. A vast cosmic realm that remains forever hidden from observation regardless of technological advancement. This isn't a temporary limitation that clever engineering might overcome. It's a fundamental physical prohibition imposed by the finite speed of light, cosmic expansion, and the universe's finite age. We're permanently trapped inside our cosmic bubble with no possibility of ever observing what lies beyond the ultimate horizon. The physics behind this cosmic censorship operates through the relentless expansion of space itself. While light from distant regions races toward us at 300 million meters per second, the space between us and those regions expands fast enough to carry some areas beyond the reach of electromagnetic communication. Regions beyond our cosmic horizon recede faster than light can travel. Not because they're moving through space at impossible speeds, but because space itself grows larger at rates that exceed light's ability to cross the expanding gap. This cosmic prohibition zone likely contains infinitely more galaxies, stars, and cosmic structures than exist within our observable bubble. Conservative estimates suggest that our visible universe represents less than 1% of the total cosmic reality that surrounds us. We might be living inside a cosmic archipelago where countless other observable universes exist beyond our detection, each centered on their own observers who see their own collections of galaxies while remaining forever invisible to us. The expansion-driven nature of this cosmic censorship means that our observable universe actually shrinks over time in terms of accessible cosmic real estate. Galaxies currently visible at the edge of our cosmic horizon will eventually recede beyond observability as cosmic expansion accelerates. Future astronomers will inherit an increasingly empty-looking universe where fewer galaxies remain visible from any given location. The cosmic prohibition zone grows larger, while the observable universe appears to become more isolated and lonely. Even more frustrating is the realization that this hidden cosmic realm might contain dramatically different physical conditions than exist within our observable bubble. The universe beyond our horizon could harbor exotic forms of matter, different values of physical constants, or entirely alien cosmic evolutionary pathway that remain forever inaccessible to scientific investigation. We're cosmic prisoners studying just a small sample of reality that happens to be visible from our particular location in space and time. This ultimate cosmic boundary represents one of the most profound limits in human knowledge. Unlike other scientific frontiers that might be overcome through technological advancement or theoretical breakthroughs, the cosmic horizon stems from fundamental properties of space, time, and causality that appear unchangeable. We live in a universe specifically designed to keep most of its contents hidden from view. It ensures that cosmic exploration will always involve studying just the fraction of reality that light has had sufficient time to reveal. The vast majority of cosmic truth lies forever beyond the physics-imposed prohibition zone that surrounds our tiny bubble of observable existence. During the first tiny fraction of a second after the Big Bang, something happened. It makes every other cosmic event look like a gentle breeze. Cosmic inflation lasted just 10 to the minus 32 seconds. It expanded the universe by a factor of at least 10 to the 26 times. Picture this comparison. If a proton suddenly inflated by the same amount, it would grow larger than a basketball. The entire observable universe today might have started smaller than a subatomic particle before this cosmic growth spurt transformed it into something unimaginably vast. This inflationary expansion operated faster than anything we observe in today's universe. During inflation, space itself expanded exponentially. It doubled in size roughly every 10 to the minus 37 seconds. That's fast enough to make light seem like it's crawling through cosmic molasses. In less time than it takes light to cross a proton, the inflating universe grew from quantum scales to dimensions larger than grapefruit. This cosmic hyperinflation happened so quickly that causality itself couldn't keep up with the expansion. The physics driving inflation involves hypothetical quantum fields that created a temporary state of cosmic anti-gravity. Unlike normal matter and energy, which slow cosmic expansion through gravitational attraction, the inflation field generated repulsive gravity. It drove space apart at exponentially accelerating rates. This cosmic repulsion operated with such intensity that it overwhelmed every other force in nature. It stretched space faster than light could travel and created the smooth, flat cosmic architecture we observe today. What makes cosmic inflation particularly mind-bending is that it potentially occurred everywhere throughout space simultaneously. The inflation wasn't centered at a particular location, but rather affected all of space equally. It created a cosmic expansion that had no center and no edge. Every point in the inflating universe experienced identical exponential growth. This transformed microscopic quantum fluctuations into cosmic scale variations that eventually became the seeds for galaxy formation. The inflationary epoch ended as suddenly as it began when the inflation field finally decayed into ordinary matter and radiation. This cosmic phase transition, called reheating, flooded the universe with the hot plasma that we observe in the cosmic microwave background. The explosive energy release from inflation's end created the initial conditions for everything that followed: star formation, galaxy evolution, and eventually the complex chemistry necessary for planets and life. This 10 to the minus 32 second cosmic explosion represents the most dramatic event in cosmic history. In less time than it takes for light to cross an atomic nucleus, inflation transformed the universe from quantum scales into a cosmic realm. It was so vast that our entire observable universe represents just a tiny fragment of the total inflated space. Here's a perspective that should make every human feel appropriately insignificant. Our entire observable universe might represent a smaller fraction of total cosmic reality than an atomic nucleus represents compared to Earth. The inflationary expansion that created our cosmic neighborhood potentially generated a universe so monumentally vast. Our 93 billion light-years wide observable bubble becomes essentially invisible within the larger cosmic architecture. Think about the scale relationships involved. An atomic nucleus measures roughly 10 to the minus 15 meters across, while Earth spans about 10 to the 7 meters in diameter. That represents a size ratio of approximately 10 to the 22 to 1. Now consider that cosmic inflation expanded the universe by factors potentially exceeding 10 to the 26. This means the true universe could be 10,000 times larger relative to our observable region than Earth is compared to an atomic nucleus. We might be living inside a cosmic speck so small it defies meaningful comparison to familiar objects. This cosmic scale relationship transforms our understanding of cosmic significance. Every galaxy, every star system, every planet we've discovered through centuries of astronomical observation exists within what amounts to a microscopic sample. It is a microscopic sample of total cosmic reality. The billions of galaxies cataloged by our most powerful telescopes represent the cosmic equivalent of a few atoms within a vast continental landmass. Our cosmic census has been limited to studying what amounts to essentially nothing in the context of true cosmic scale. The implications become even more staggering when you consider cosmic evolution. All the stellar formation, galactic mergers, and cosmic chemical enrichment we observe occurred within this infinitesimally tiny sample region. The entire 13.8 billion year history of cosmic evolution that astronomers have painstakingly reconstructed describes events occurring within a cosmic volume. That volume represents essentially 0% of the total space created by inflation. We've been studying cosmic evolution within what amounts to a single grain of sand on an infinite cosmic beach. What makes this scale comparison particularly humbling is the realization that our observable universe contains roughly 2 trillion galaxies, each hosting hundreds of billions of stars, many supporting planetary systems that might harbor life. This cosmic abundance that seems almost infinite from our perspective represents just the tiniest possible sample of what inflation potentially created. The true cosmic inventory of galaxies, stars, and potentially habitable worlds could exceed our observable cosmic census. It could exceed it by factors so large they have no meaningful comparison to anything in human experience. This cosmic scale hierarchy suggests that our entire scientific understanding of the universe derives from observing essentially nothing. Every physical law, every cosmic evolutionary model, every theory about the universe's fate has been developed by studying a sample region. That region is so microscopically small that it provides virtually no information about the true cosmic whole. We're cosmic microbes attempting to understand the nature of reality based on observations limited to our immediate microscopic neighborhood. Precision measurements of cosmic geometry reveal something that should make mathematicians and philosophers equally nervous. Our universe appears to be perfectly flat. This cosmic flatness is measured to within 0.4% accuracy by satellite missions studying the cosmic microwave background. It suggests that space extends infinitely in all directions. It does so rather than curving back on itself like the surface of a cosmic sphere. If these measurements are correct, we inhabit an infinite universe containing unlimited amounts of matter, energy, and potentially every possible cosmic configuration. Cosmic flatness represents one of 3 possible geometric configurations for the universe. A positively curved universe would eventually curve back on itself like the surface of a sphere. It would create a finite cosmic volume despite having no edges or boundaries. A negatively curved universe would extend infinitely while exhibiting saddle-shaped geometry that causes parallel lines to diverge. Our universe's measured flatness indicates the critical boundary condition between these alternatives. Infinite extent with Euclidean geometry, where parallel lines remain parallel across cosmic distances. The measurement precision required to determine cosmic curvature pushes observational astronomy to its absolute limits. Satellite missions analyze temperature fluctuations in the cosmic microwave background radiation that differ by just millions of degrees across different angular scales. These tiny variations reveal geometric signatures that indicate whether space curves inward, curves outward, or remains perfectly flat across the observable universe. Current measurements consistently indicate flatness to within observational uncertainty. But here's where cosmic flatness becomes truly mind-boggling. If the universe is truly infinite, then it contains infinite amounts of everything. Infinite galaxies, infinite stars, infinite planetary systems, infinite copies of Earth with infinite variations of human history. Mathematical analysis suggests that in an infinite flat universe, every possible cosmic configuration must occur infinitely many times across infinite space. Somewhere in the infinite cosmos, there exist perfect duplicates of our observable universe, along with versions containing every possible variation of cosmic history. The infinite universe hypothesis also implies that beyond our cosmic horizon lie regions where the laws of physics might operate differently. Cosmic evolution may have followed entirely different pathways. Infinite space provides unlimited room for cosmic experimentation. It potentially harbors regions with different values of physical constants, alternative forms of matter, or exotic cosmic structures impossible within our observable cosmic neighborhood. The flat universe measurements hint at a cosmic reality so vast and varied that it exceeds even our wildest theoretical speculation. What makes cosmic flatness particularly unsettling is its apparent fine-tuning. The universe's density sits precisely at the critical value that produces flat geometry, not slightly higher, which would create positive curvature, or slightly lower, which would generate negative curvature. This cosmic balance appears so precisely calibrated that it suggests either extraordinary cosmic coincidence or some deeper principle that naturally produces flat geometry. The flat universe measurements reveal a cosmos that appears specifically designed to extend infinitely while maintaining the simplest possible geometric structure. Eternal inflation represents cosmology's most ambitious and terrifying theory, the possibility that the inflationary expansion that created our universe never actually ended but continues forever. It constantly spawns new cosmic regions like a celestial assembly line that operates at infinite capacity. According to this theory, what we call the universe is actually just one bubble in an infinitely expanding cosmic foam. New universes constantly form, expand, and evolve while remaining forever isolated from each other by the ongoing inflationary expansion. The mechanism driving eternal inflation operates through quantum fluctuations in the inflation field itself. Most regions of inflating space eventually exit the inflationary phase and become normal cosmic domains like our observable universe. But quantum mechanics ensures that some regions continue inflating indefinitely. These eternally inflating zones generate new pocket universes where inflation ends and normal cosmic evolution begins. They create an infinite hierarchy of cosmic bubbles embedded within the ever-expanding inflationary background. Each pocket universe formed through eternal inflation develops its own distinct cosmic properties that might differ dramatically from our local cosmic neighborhood. The physical constants, fundamental forces, and even the number of spatial dimensions could vary between different cosmic bubbles. Some pocket universes might harbor more efficient star formation, faster cosmic evolution, or entirely different forms of matter and energy. Others might prove completely hostile to complex chemistry. They would remain sterile cosmic domains where nothing interesting ever develops. The scale relationships involved in eternal inflation defy human comprehension. Our entire observable universe represents just one temporarily stable bubble within an infinitely larger inflationary ocean. The spacing between neighboring pocket universes likely exceeds our cosmic dimensions by factors so large that they make previous scale comparisons seem modest. Each cosmic bubble evolves in complete isolation. It remains forever cut off from communication with other pocket universes by the accelerating expansion of the intervening inflationary space. What makes eternal inflation particularly unsettling is its complete lack of observational consequences within our cosmic bubble. The theory predicts that we should observe exactly what we do observe: a single pocket universe with no evidence of other cosmic domains. The inflationary expansion between pocket universes operates faster than light speed. This ensures that information from neighboring cosmic bubbles can never reach our observational instruments. We're trapped within our cosmic bubble with no possibility of detecting the infinite cosmic archipelago that might surround us. Eternal inflation also raises profound questions about cosmic uniqueness and the nature of physical reality. If infinite pocket universes exist with varying physical properties, then every possible combination of cosmic conditions must occur infinitely many times. It must occur across the eternal inflationary landscape. Our universe's apparent fine-tuning for complexity in life becomes inevitable rather than remarkable. Among infinite cosmic variations, universes like ours must exist regardless of how improbable they might seem from our limited perspective. The eternal inflation theory transforms cosmology from a study of the universe. It becomes an investigation of cosmic natural selection operating across infinite space and time. We inhabit just one temporary island in an infinite cosmic ocean. New universes constantly form while others evolve, age, and potentially fade into cold, empty darkness. Our cosmic home represents just one momentary configuration in an eternal cosmic process. It generates unlimited variety across scales that exceed human imagination or meaningful comprehension. After decades of searching with our most powerful telescopes and detection methods, astronomers have made a discovery that should humble or terrify every person alive. Earth remains the only confirmed planet where life exists among the estimated 200 billion trillion stars in the observable universe. Despite finding thousands of exoplanets, detecting potentially habitable worlds, and identifying planets with Earth-like characteristics, we haven't found a single definitive example of life beyond our own planet. In a cosmos containing more stellar systems than grains of sand on every beach on Earth, life has been confirmed in exactly one location. This cosmic loneliness becomes even more staggering when you consider the enormous effort invested in the search for extraterrestrial life. Radio telescopes scan the skies for artificial signals. Space missions analyze Martian soil samples for biosignatures. The Kepler Space Telescope catalogues thousands of potentially habitable exoplanets. Advanced spectroscopic techniques probe the atmospheres of distant worlds for oxygen, methane, and other gases that might indicate biological activity. Yet despite these sophisticated search strategies, Earth continues to represent a sample size of exactly 1 for confirmed biospheres in the universe. The failure to detect life elsewhere isn't due to lack of trying or inadequate technology. Our current instruments can detect industrial civilizations across galactic distances through their radio emissions. We can identify biosignature gases in exoplanet atmospheres located hundreds of light years away. Advanced optical telescopes could potentially detect city lights on the night sides of nearby exoplanets. The absence of confirmed detections suggests either that life is extraordinarily rare, that intelligent civilizations remain well hidden, or that Earth occupies a uniquely privileged position in the cosmic hierarchy. What makes Earth's biological uniqueness particularly remarkable is the apparent commonality of potentially habitable worlds. Astronomers estimate that roughly 20% of Sun-like stars host planets within their habitable zones. Liquid water could exist on planetary surfaces. The Milky Way alone should contain billions of potentially life-bearing worlds. Yet among this vast cosmic real estate market of habitable planets, only Earth has produced the complex chemistry, stable climate, and protective conditions necessary for biology to flourish for billions of years. The cosmic census reveals a universe that appears specifically designed to create planets, but remarkably ineffective at populating them with life. Rocky worlds form readily around most stars. Atmospheric evolution creates diverse planetary climates. Chemical processes generate complex molecular libraries on planetary surfaces. Yet the final step, the emergence of self-replicating chemistry that we call life, appears to represent an extraordinarily rare cosmic achievement. It might occur only once among trillions of otherwise promising planetary experiments. This biological isolation places Earth in the cosmic equivalent of winning the ultimate lottery. Among 200 billion trillion opportunities for life to emerge across the observable universe, our planet achieved the apparently near impossible transition from complex chemistry to biology. We live on the universe's most successful biological experiment. We are surrounded by a cosmos filled with sterile worlds. They never quite manage to kindle the spark of life, despite having billions of years and ideal conditions for experimentation. Human beings represent one of the universe's most remarkable achievements in scale transcendence. A typical person measures roughly 2 meters tall. Individual atoms span about 10 to the minus 10 meters across. Meanwhile, the observable universe extends 4.4 times 10 to the 26 meters from edge to edge. This means that humans sit almost exactly halfway between atomic and cosmic scales on a logarithmic scale. We're simultaneously 10 to the 10 times larger than atoms. We're also 10 to the 25 times smaller than the cosmic realm we can observe and comprehend. What makes this scale relationship truly extraordinary is humanity's ability to understand physical phenomena across this entire range. We can probe the quantum behavior of subatomic particles through sophisticated experiments. We can model the gravitational dynamics of galaxy clusters containing trillions of stars. We develop theories that predict both the electronic properties of semiconductor devices and the cosmic evolution of the universe across billions of years. Somehow, matter organized into human scale structures has become capable of comprehending physical reality across 35 orders of magnitude in scale. This cognitive scale jump represents perhaps the most improbable achievement in cosmic history. Humans are trying to understand a universe that's 10 to the 25 times larger than their physical size. They do it using brains composed of roughly 10 to the 11 neurons. Each neuron measures about 10 to the minus 5 meters across. Our neural networks occupy volumes of approximately 10 to the minus 3 cubic meters. Yet they generate models that describe cosmic structures spanning 10 to the 78 cubic meters of space. The ratio between cosmic scale and human brain scale exceeds the ratio between human size and subatomic particles. The physics enabling this scale transcendence remains mysterious even to neuroscience researchers. Human consciousness somehow emerges from electrochemical processes within networks of biological cells. Yet these same neural processes can comprehend abstract concepts like cosmic inflation, dark energy, and multidimensional geometry. Brains built from atomic matter successfully model atomic behavior. Neural circuits evolved in Earth's gravitational field accurately predict the gravitational evolution of cosmic structures across billions of light years. What makes human-scale comprehension even more remarkable is its recent emergence in cosmic history. Homo sapiens developed the cognitive capacity for scientific reasoning just 300,000 years ago. Roughly about 0.02% of the universe's total age. In less than 400 years since Galileo first pointed a telescope skyward, human civilization has mapped cosmic structure from subatomic particles to the cosmic microwave background. We've achieved this unprecedented scale comprehension using technologies developed during a time period. That period represents less than 1/1,000,000th of cosmic history. The scale jump achieved by human cognition suggests that consciousness might represent one of the universe's most improbable organizational achievements. Among all possible arrangements of atomic matter, only an extremely narrow range of configurations can generate the information processing capabilities necessary for cosmic comprehension. Yet somehow, through biological evolution operating on a single planet orbiting an ordinary star, matter accidentally organized itself into structures capable of understanding the entire cosmic architecture that contains them. We are the universe's attempt to understand itself through the cognitive achievements of temporarily organized atomic matter. Modern human civilization represents one of the briefest footnotes in the universe's 13.8 billion year story. Homo sapiens emerged roughly 300,000 years ago. Recognizably, modern human behavior developed just 50,000 to 100,000 years ago. Complex language, artistic expression, technological innovation, and scientific reasoning appeared relatively recently. Written history spans merely 5,000 years. The scientific revolution that enabled our understanding of cosmic scale began just 400 years ago. All of human achievement fits within about 0.07% of the universe's total lifetime. Picture the entire history of the universe compressed into a single calendar year. Modern humans would appear during the final few seconds of December 31st. The agricultural revolution would occur in the last 1/10 of a second. The scientific revolution would fit within the final 100th of a second. All of recorded human history, every civilization, every scientific discovery, every technological achievement would flash by in less time than it takes to blink. We are cosmic newcomers who arrived at the very last moment of an incredibly long cosmic story. This temporal compression reveals how recently the universe developed a capacity for self-awareness. For about 13.8 billion years, cosmic evolution proceeded without any conscious observers capable of studying stellar formation, galactic evolution, or cosmic expansion. Stars formed and died. Galaxies merged and separated. Cosmic structures evolved across billions of years without any witnesses capable of understanding the magnificent cosmic architecture around them. The universe remained unconscious of its own existence until the final cosmic instant. What makes humanity's late arrival even more remarkable is how quickly we've progressed from cosmic ignorance to comprehensive cosmic understanding. Ancient humans looked up at the night sky and saw scattered points of light. They had no understanding of their true nature or distances. Just 400 years later, we've measured the universe's age, mapped its large-scale structure, and developed theories describing its evolution from quantum fluctuations to the complex cosmic web we observe today. The transition from cosmic ignorance to cosmic comprehension occurred in roughly 1/1,000,000th of the time humans have existed on Earth. The brief duration of human cosmic awareness also highlights how precarious our current understanding might be. Climate change, asteroid impacts, supervolcanic eruptions, or nuclear warfare could end human civilization within the next few centuries. If humanity disappeared tomorrow, the universe would continue evolving for trillions of years without any conscious observers capable of appreciating its ongoing evolution. Our window of cosmic consciousness might represent just a brief flicker in an otherwise unconscious cosmic story stretching across infinite time. Yet despite our recent arrival and uncertain future, humans have achieved something unprecedented in cosmic history: the development of conscious beings capable of studying and understanding the universe that created them. We represent the cosmic process becoming aware of itself through the cognitive achievements of temporarily organized matter. In the brief cosmic instant since modern humans appeared, we've transformed from unconscious participants in cosmic evolution into conscious students of cosmic architecture. We've achieved a level of cosmic understanding that required 13.8 billion years of cosmic evolution to make possible. Faced with a universe so vast it reduces human existence to cosmic insignificance, humanity responds not with despair but with an almost defiant determination to explore, understand, and map every accessible corner of cosmic reality. This exploring drive represents one of the most remarkable characteristics of human consciousness: the tendency to become more curious and ambitious when confronted with larger scales. Rather than becoming overwhelmed by cosmic immensity, we are a species that looks at infinite space and starts building telescopes. The scope of human cosmic exploration achievements should impress any rational observer. We've sent robotic ambassadors to every planet in our solar system and beyond. We've mapped the cosmic microwave background radiation with precision instruments. We've detected gravitational waves from black hole collisions occurring billions of light years away. We've discovered thousands of exoplanets orbiting distant stars. We've traced cosmic evolution from the first fraction of a second after the Big Bang to the present epoch of expansion. All of this exploration occurred within just a few centuries of serious scientific investigation. What makes human exploration particularly remarkable is how we've overcome the physical limitations imposed by cosmic scale through technological innovation. Unable to travel to distant stars, we've built instruments that capture ancient starlight. It carries information about cosmic conditions billions of years ago. Unable to observe black holes directly, we've developed gravitational wave detectors. They reveal black hole mergers through ripples in space-time itself. Unable to visit other galaxies, we've created space telescopes. They provide detailed observations of galactic evolution across cosmic time. The human response to cosmic vastness also reveals something profound about consciousness itself. Rather than being intimidated by scales that dwarf human significance, human minds seem naturally drawn to tackle the largest possible questions about cosmic reality. We study problems involving infinite space, eternal time, and multiple universes despite being finite beings with limited lifespans. Human curiosity scales up to match whatever cosmic challenges we discover. This suggests that consciousness might be designed for confronting arbitrarily large conceptual problems. Human cosmic exploration continues accelerating despite mounting evidence of our cosmic insignificance. Every new discovery revealing larger cosmic scales or longer time periods seems to motivate additional exploration. It does not discourage further investigation. We respond to the discovery of dark energy by planning more sensitive surveys. We react to evidence for cosmic inflation by developing theories about eternal inflation and multiple universes. Human ambition appears to grow in proportion to cosmic complexity rather than being diminished by it. Perhaps most remarkably, humans continue cosmic exploration, knowing that most cosmic truth will forever remain beyond our reach. The physics-imposed limits on observation don't discourage human curiosity. They inspire more creative approaches to investigation. Unable to observe beyond the cosmic horizon, we develop theories about what might lie in unobservable regions. Faced with questions that can't be answered through direct observation, we create mathematical models that explore logical possibilities beyond empirical access. This unstoppable drive to explore and understand represents humanity's ultimate response to cosmic scale. We are matter that has organized itself into configurations capable of studying the cosmic process that created us. Despite occupying infinitesimally tiny volumes of space for microscopically brief periods of time, human consciousness has achieved something unprecedented. The development of cosmic perspective that transcends the physical limitations of our material substrate. We have become the universe's way of understanding itself. We transform cosmic insignificance into cosmic significance through the simple act of refusing to be intimidated by infinite scales.